Chapter 7 Homework 7.1 For the given 2D plane stress state, and shown here, 9 megapascal tensile along X, 3 megapascal tensile along vertical Y, and 4 megapascal of shearing stress, as illustrated, going down in this plane, going the other way in the other plane. Okay, we want you to determine the principal stresses in that plane, within that plane. The orientation of principal axis in that plane. Okay, where, in which plane, in which direction does the principal axis occur? The maximum in-plane shearing stress, just the in-plane, not the three-dimensional, just the in-plane, and the orientation of the plane for maximum shearing stresses. And finally, the corresponding normal stress for those planes where maximum in-plane shearing stress occur. Okay, so this is our 2D plane stress state. To solve this, you can use the equation, but here I'm using the Mohr circle method. So this is our plane stress state. Tensile 9 megapascal along X, tensile 3 megapascal along Y, and the shearing stress of 4 megapascal as labeled. So based on these, we would know the coordinates for two related points. The coordinates for two related points. The first one would be capital X, corresponding to the horizontal x-axis. Okay, the capital X corresponding to the horizontal x-axis, we know 9. Okay, that's the first coordinate, and the shearing stress of 4, and it's trying to rotate this block clockwise based on the convention for Mohr circle. We call it positive 4. So 9, 4 for the coordinate of the first point, capital X on the Mohr circle. And also, we would be able to know for vertical Y, we would know the coordinate for the capital Y, and the tensile M, that will be the first coordinate, and the shearing stress of 4 megapascal trying to rotate this element counterclockwise based on the sign convention for the Mohr circle. We would call it -4. Okay, so now we know the coordinates for the two related points on the Mohr circle. We said not arbitrary points, but two related points. And when you connect these 2 points, this goes through the center for this circle. Okay, and where is this center? So 9, 3, average would be 9 plus 3, 12 divided by 2. The horizontal would be 6, and the positive 4, negative 4, the vertical would be 0. So the center for this Mohr circle would be C at 6, 0. Okay, so 9, 4, 6, 0. So the distance from C to here would be 9 minus 6 would be 3 from here to here. Vertical from here to here would just be 4. So 3 horizontal, 4 vertical for this triangle. So the radius CX would be 5. The radius would be 5 for this Mohr circle. So once we know the center, once we know the radius, we would be able to know the coordinate for the A point. It would be center plus radius. Center is 6, radius we said is 5, so the A coordinate would be 11. So the maximum tensile stress in this plane would be at A point, and it would be 11 megapascal. Okay, the minimum tensile stress would be the other direction, which is center minus the radius. The center is at 6, 0. The radius we said is 5, so the B point would be 6 minus 5, it would be 1 megapascal, still tensile. Minimum tensile stress, and vertical, of course, is 0. Okay, so now we know the principal stresses in this plane. The next is about where are these principal stresses? In which direction in this plane where can we find the maximum normal and the minimum normal? Okay, so we still go use the Mohr circle method, and we know 9, 4 for X, 6, 0 for C. From X to A, how do you find A? You rotate from X on Mohr circle clockwise by this 2 theta P angle to find A. Okay, from X to find A, you rotate clockwise by this 2 theta P to find A. And what about this 2 theta P that we know? Okay, from here to here, vertical, we said it's 4. From C to here, we said it's 3. So the tangent of 2 theta P would be 4 over 3. Tangent to theta P would be 4 over 3. So theta P would be half of A tangent of 4 over 3. And that gives out to be 0.464 reading. 0.464 reading. And if we can convert that into degree, it would turns out to be 26.6 degree. Okay, so it means from in Mohr circle to go from X to A, we would rotate 2 theta P. So in real geometry, to find A, we would rotate from horizontal X by half of 2 theta P, or theta P, which is 26.6 degrees. Theta P 26.6 degree. We would find A. And this maximum tensile stress, as we said, would be 11 megapascal. Okay. Similarly, to find B. You can start from Y. You rotate similarly clockwise by same 2 theta P, and which means in real geometry, to find B, you would start from vertical Y, rotate in the same fashion. Y to B is clockwise, same fashion clockwise, and the exact angle is the same of 26.6 degree of theta P to find the minimum normal stress, represented by B, and that turns out to be just 1 megapascal. Okay, that's the minimum normal stress in this plane. So once we have the Mohr circle, we know X and Y, we then know the center C, and we also know the radius, and we know A and B maximum tensile, minimum tensile. So the maximum shearing stress would be, in plane shearing stress would be just the top of the Mohr circle or the bottom, which would be D point or E point, but the absolute value for the maximum shearing stress would just be radius, which would be just a 5 megapascal. Okay, and then where are they? Well, the to find the D point, you can still rotate from X, but it would be rotate counterclockwise. From X to D, that is rotate counterclockwise, and you can do that from X to D, or once you find A, you can rotate from A counterclockwise on Mohr circle 90, which means in real geometry 45 degrees from A to find D, or from B to find E. On the other hand, if you start from horizontal x, that would be you rotate from x to d counterclockwise by 45 minus this angle. It would turn out to be 18.4 counterclockwise from x to reaching d, or from y to reach e. Okay, so again, this is your horizontal. If you start from this, you rotate counterclockwise by theta s, and what is theta s? We said it's 45 minus 26.6 degree, which is turned out to be 18.4 degree. You would be able to find the direction and the plane where our shearing stress reaches maximum. It would be 5 megapascal. Okay, and then finally we are asking the corresponding normal stress for the plane where the shearing stress reaches maximum. It will be just the horizontal coordinate for the D point or for the E point. It will just be the center, which is 6 megapascal. It will be just the average of the 6 megapascal. Okay? Homework 7.2. Given the original 2D plane stress state as illustrated, we want you to determine the normal and shearing stress for a new orientation or local element rotated A 26.6 degree clockwise, okay, or 30 degree counterclockwise, okay. For two scenario, one is rotate clockwise by 26.6 degree, the other is rotate counterclockwise by 30 degree. Okay, you can solve this problem using either the equation set and shown in lecture slides, or you can use the Mohr circle method. And I'm going to illustrate both methods. First, let's try to solve it using the equation sets given on the lecture slides earlier. So for A, to rotate 26.6 clockwise. Therefore, to use the equation set, the 2 theta would be 2 times the angle 26.6, and we put a negative sign because when we said to use the equation set, we define as angle rotation counterclockwise as positive. So if we rotate clockwise, it will be negative. It will be negative 53.2 degree for the 2 theta value. Okay. Similarly, to use the equation set, the sign convention for the shearing stress is also opposite in Mohr circle. Okay. For this shearing stress of 4 megapascal, if we are going to use Mohr circle, we call this part positive because it's trying to rotate clockwise. But if we're going to use the equation set, remember we said it's opposite. If it goes up, we call it positive. So this one is rotating it the other way. We call it a negative 4. Okay, or you call it tau xy, which means in the plane perpendicular to x-axis, but it's opposite to the y, so it will be negative y. So if we're going to use the equation set, it will be instead of 4, it will be negative 4 megapascal for tau xy. So now let's look at our equation. Tau xy prime from the equation set would be average of tau x and tau y plus the difference of tau x minus tau y divided by 2 times cosine 2 theta plus sigma x minus sigma y, and here is tau xy times sine 2 theta. Okay, and you plug the number in. Sigma x would be 9, sigma y would be 3, and the plus here, minus here, and the 2 theta we said is 53.2 degree, but don't forget the negative sign because it is clockwise. It is clockwise, which is opposite to the sign convention when for the equation set. Okay, so we put negative here. The tau xy is also negative, and 2 theta also negative. And plug the number in, you would get the sigma, the normal stress for the new orientation, which is 26.6 degree clockwise, would be 11 megapascal. Similarly, for 2 theta, again it's minus 53.2 degree, and tau x prime y prime would be given by that equation, but in that equation the 2 theta would be negative. The tau xy, again similar to before, would be negative 4, and you would get tau x prime y prime would be approximately 0 megapascal. Okay, and then for the normal stress in the new y direction of tau sigma y prime would also be given in the previous equation. Average, this is would be minus of the difference, and tau xy again would be minus, 2 theta would be minus. You plug the number in, you would get sigma y prime for the new orientation would be 1 megapascal. Okay, so this way we know the result for the new orientation, that is 26.6 degree clockwise from the original orientation. On the other hand, if we are going to rotate the element 30 degree counterclockwise, okay, then the 2 theta would be positive because we are rotating according to the sign convention. The 2 theta would be 2 times 30 degree would be 60 degree, and the shearing stress again for the original tau xy would be minus 4, and then the sigma x prime would be average plus the difference divided by 2 times the cosine 2 theta plus tau sine 2 theta. And if you plug the number in, you would get 4.04 megapascal. And the new shearing stress tau x prime y prime would be minus the difference divided by 2 times sine 2 theta, which is 60 degree, plus the shearing stress in the original direction times cosine this angle. Okay, and you plug the number in, it will be minus 4.60 megapascal. And finally, tau y prime, the normal stress in the new y direction, if you plug the number in, it would be 7.96 megapascal. So this would be our new orientation. The x is rotated 30 degree counterclockwise from the original x, and you can find normal stress in the new x, normal stress in the new y, and the shearing stress in the new orientation. Okay. Similarly, you can solve the problem using Mohr circle. Again, this is your original stress state. We start with the original stress state. We can get the coordinate for correlated points. This is 9, we play 9, and for Mohr circle, this is trying to rotate clockwise. It would be 9,4, and for the y direction, it would be 3 here, comma, and it's trying to rotate the counterclockwise, would be -4. Okay, so with these 2 points, we would be able to get the center, which is 9 plus 3 is 12 divided by 2, which is 6, comma 0. And then this is a center. We know the 2 coordinates that when you connect go through the center, we will know the geometry here. This is 4, this is 3. We will know this angle would be 53.2 degrees. Then we said the new orientation is clockwise 26.6 from X. Okay, so if clockwise and on real geometry you rotate 26.6, which means in Mohr circle you rotate 26.6 times 2, which is 53.2 degrees, and you would exactly onto X prime, and that X prime is exactly at the horizontal intercept, and that would give us the center plus radius, which is 11, and from the original y you rotate for the same fashion you find the y prime, which is also the same as B point. It would be center minus radius, which is 1 megapascal. And tau xy for x prime y prime for this new orientation, it will be 0. Okay. On the other hand, if we want to solve for the situation when we rotated counterclockwise 30 degrees from x, this is x. In real geometry, rotate 30 degrees counterclockwise, which means on Mohr circle you also start from x, rotating the same fashion counterclockwise, but double the angle, which from 30 to 60. Okay, from here to here is, from here to here is 60. So on Mohr circle we know this angle is 53.2 plus another 60. That will be 13.2 degree to find the x prime. Okay, that's from x. From y, rotate similarly by 60 degrees, you find the y prime. And what are its coordinates? It will be center plus this. It will be 6.0 plus this. What is this? It will be the radius times the cosine for that angle. Okay, cosine for that angle. That angle is 53.2 plus 60, 113.2, and then this x double prime would be 6 plus radius times cosine of 113.2, and that turns out to be 4.03 megapascal. And the new y double prime would be y rotate counterclockwise by 60. It will be 6 minus cosine 113.2. It will be 7.97 megapascal, because this cosine number would be negative. Okay, a negative you get larger than the original value, and the tau xy prime would just be this phi times this angle, sine for that angle. It will turn out to be 4.60 megapascal, and these result matches what we got exactly earlier. Homework 7.3. For the state of plane stress shown, we want you to determine the maximum 3D shearing stress. When we say 3D, you may have to consider both in-plane and out-of-plane shearing stress. For two scenarios, one is when sigma y is 1 megapascal, sigma x would be 7 megapascal. Another scenario is when sigma y is 3 megapascal and sigma x is 9 megapascal. Okay, so this is our plane stress state. We give you the shearing stress for the normal. We said two scenarios. For each of the scenarios, we want to determine the maximum 3D shearing stress. So first, for the first scenario, when y is 1, sigma y, and sigma x is 7. So this is our plane stress state. We can solve this by Mohr circle. With this local plane stress state, we know the coordinates for two related points on the Mohr circle. For x, it will be 7, comma, the 4 shearing stress is trying to rotate it clockwise, so positive 4. For the y, we would have 1, comma, the shearing stress is trying to rotate it counterclockwise for this one, so it will be -4 for the sign convention for Mohr circle. So x and y, we know the coordinates. So where is the center? We said these 2 points are not arbitrary. They are, when you connect these 2 points, they should go through the center, and the center should be on the horizontal axis. So 7, 1, the center would be 7 plus 1 divided by 2, 4, comma, positive 4, negative 4, the other would be 0. Okay, once we know the x, the y, and the c, next we will know the radius. So 7 here, 4 here, so the distance horizontally it would be 3, vertical would be 4, so the radius would just be 5 or 5 megapascal. Okay, and this is our Mohr circle, x and the y. And based on this this xy circle and the maximum normal stress and the minimum normal stress are at opposite sign. The maximum in-plane normal stress are opposite sign, which means we can draw 3 circles, one here, and one is the original xy or AB. Because they are opposite sign, we already draw the 3 circle, and the maximum 3D shearing stress would be just the in-plane shearing stress, and it will just be the radius, which would be 5 megapascal. So the maximum 3D shearing stress would just be the radius for the largest circle, which is also the xy circle, and it will be just the 5 megapascal. On the other hand, if sigma y would be 3, sigma x would be 9, so 9, 3, and 4. Again, we would know the coordinates for two related points. For x would be 9, comma, 4. For y, it would be 3, comma, rotating counterclockwise, -4. So again, we also know the coordinates for two related points, and when you connect the center, it would be 9 plus 3, 12 divided by 2, 6, comma, 0. And again, 9, 4, 6, 0, the horizontal, for this special triangle, the horizontal would be 3, the vertical would be 4, the radius would be 5. But for this xy plane or circle, the maximum in plane normal stress and minimum in-plane normal stress are the same sign, which means if we construct the three more circle, one would be this XY circle or AB circle, that will be the BO circle, but then there will be a larger AO circle, and then the maximum 3D shearing stress would be the radius for this outer circle, and that radius would just be half of AO, which is C plus radius, which is 6 plus 5, which would be 11, and half of it would be 5.5 megapascal. This way, we would be able to determine the maximum 3D shearing stress. If our local plane stress is this, the maximum in-plane shearing stress would be slightly smaller than the maximum 3D shearing stress. The 3D one maximum shearing stress would be 5.5, while the in-plane max would be only 5 megapascal. Okay. Homework 7.4. A spherical container made of steel has 20 feet outer diameter and a wall thickness of ½ inch. Knowing the internal pressure is 50 psi pound per square inch, we want you to estimate the maximum normal stress and the maximum shearing stress in the container's wall. Okay, the spherical container, 20 feet diameter or 10 feet radius, wall thickness ½ inch, internal pressure 50 psi. We want to know the maximum normal and maximum shearing stress in the container wall. So from what we learned before, for spherical container, the in-plane normal stress in the wall sigma 1 and sigma 2 are the same. It would be PR over 2T. P is internal pressure, R is spherical container radius, T would be the thickness, and in this case P would be 50 psi, R for radius would be 10 foot, converted that into inches times 12 inches, and 2T would be ½ inch, 0.5 inch, and you do the math, it would come out to be 6,000 psi. So 6,000 psi in the container wall in two directions, in plane directions. So as we said, the Mohr circle for the container wall would be the corresponding shearing stress are both 0 for those two arbitrary direction perpendicular. So the 2 points on the Mohr circle are just x and y are the same. One would be so the two coordinate would be 6,000 0, 6,000 0, and the maximum normal stress would just be this A B point. It would be the same as sigma 1 would be 6,000 psi, and the maximum shearing stress would be half of it, half of this AB location, or 0.5 of this sigma 1. It would turn out to be 3,000 psi. Okay. Finally, homework 7.5. A 4-meter diameter, 10-meter tall, cylinder-shaped storage tank has wall thickness of 10 millimeter. Okay, 4 millimeter in diameter, 4 meter in diameter, 10 meter tall, and 10 millimeter thick wall. We want you to calculate the maximum normal stress and the maximum shearing stress in the cylinder wall, side wall, when the tank is filled all the way up with water. Okay, when the tank is filled all the way up with water. So when the tank is filled up with water, the hydraulic pressure, what we learned from physics is rho gh. Hydraulic pressure is rho gh. H is the depth, g is the gravity, and rho is the density. Okay, and of course the highest stress would be occurring at the largest depth, which is at the bottom on the sidewall. Okay, so rho gh, if it's 10-meter tall, rho gh for water, rho would be 1,000 kilogram per cubic meter. G is 9.8 meter per second squared, and H would be 10 meter for the bottom of the storage tank, and that comes up to be 1010. So 9.8 times 10 to the power of 4, and in the unit of kilogram times meter per second squared divided by, this is 1/meter cube, meter, so 1/meter squared, and kilogram mass times meter per second squared, that is essentially Newton. Okay, so the pressure would be 9.8 times 10 to the power of 4 Newton per meter square, or 9.8 times 10 to the power of 4 Pascal. Okay, so that is our hydraulic pressure. For a cylindrical shaped vessel, we know that the hoop press sigma 1, hoop press is along the circular direction for the cylindrical vessel, would be PR/T. This hoop stress prevent the cylinder gets larger in diameter. Okay, PR/T pressure would be 9.8 times 10 to the power of 4 Pascal. R would be radius. We said 4-meter diameter, radius would be 2 meter, and the wall thickness is 10 millimeter or 1 centimeter or 0.01 meter. We plug the number in, we would get the hoop stress would be 19.6 megapascal. Okay, the longitudinal stress, which is along the long axis for this cylindrical vessel, would be PR/2T. Okay, the longitudinal stress help prevent the cylinder gets longer, and that would be 9.8 times 10 to the power of 4 Pascal times 2 meter over 2 times the thickness, and it comes out to be also 9.8 megapascal. Okay, so we now know for the local point that will be the hoop stress along the circular direction, and that will be the longitudinal stress along the axial direction. So we will know the 2 points on the Mohr circle. One is x, is essentially here 0. It will be 19.6 megapascal. Okay, it's trying to make the cylinder larger in radius. The other one is y, is or this we can call it B point, 9.8 megapascal, and also 0. Okay, so we know the 2 points on the Mohr circle, and we can construct in 3D the 3 Mohr circle. One would be this one, the other would be BO, the other one would be AO. So the maximum normal stress in 3D would just be the hoop stress would be 19.6 megapascal. The maximum shearing stress in 3D would be half of the sigma 1, or the D prime point. It would be 9.8 megapascal, or half of sigma 1. Okay.